In this video, we're discussing tangent planes. So we're trying to find a plane that is tangent to a given surface at a given point. So in this video, we will derive the formula for the tangent plane, which is really about finding the formula for the normal vector. And then we'll do a couple of examples. And these will be examples of surfaces that we can actually sketch so that we can see what's going on. Okay, so let's talk about this idea of a tangent plane. If I have a surface given by z equals f of xy, it looks like this. Every xy in the domain is associated with a z value, and as we plot all of those points, as xy goes through its entire domain, we get all of those different z values, we get a surface, and it might look like this. Now what we're trying to derive the formula for at this point is the tangent plane to the surface at a particular xy pair. So we want the tangent plane at x naught, y naught. So we substitute in x naught, we substitute in y naught. To get the corresponding z value, we evaluate f of xy at x naught, y naught. So we want a tangent plane right there that goes through x naught, y naught, and z naught, which is f of x naught, y naught. And let's talk about what that tangent plane is. A tangent plane is the plane that contains all of the tangent vectors to the surface at that point. You'd say, well, what do you mean all the tangent vectors? Well, if I'm on this surface, I can sketch a curve, like that curve C given by r of t, and this is in three-dimensional space, so it has components x of t, y of t, and z of t. And at this point, x naught, y naught, z naught, oops, doesn't look like that, it's going to have a tangent vector. It's pointing in the direction of motion along that curve. We want the plane that contains that tangent vector. And we want the plane that contains the tangent vector for this other path too. Maybe I'm on that path. At that point, the tangent vector would be this. So I need a plane that contains all the tangent vectors. Now to find any plane, we need two things. We need a point on this plane, and we also need a normal vector to the plane. The first thing we're going to do is derive the equation for the normal vector for a tangent plane to the surface. Okay, so let's talk about how we would do that. Now, it's convenient to write the equation for the surface a little bit differently. We've been thinking of z as a function of two variables. We could also think of this surface in a different way. We could think of it as a level surface of some function of x, y, and z. So we're going to let capital F of x, y, z equal z minus little f of x, y. And if you're saying to yourself, but those are the same, aren't you just going to get 0? You're right, you are going to get 0. So this is a level surface of this function of three variables. I've got f of x, y, and z equals 0, and that represents a surface. So rather than using this form of the equation of the surface, we're going to use this form. A lot of students look at this and they're like, what do you mean, Miss Townsend? Well, let me just give you a quick example. If z equals x squared plus y squared, that's our elliptic paraboloid facing up. Looks like this. Well, instead of writing it as z equals x squared plus y squared, we're going to define a new function, f of x, y, z, and we'll make it z minus this quantity. So z minus x squared minus y squared equals 0. So rather than describing this surface this way, we're going to describe this surface this way, as z minus x squared minus y squared equals 0. I know that you can see that this equation is equivalent to this equation. We're just thinking of it differently. Instead of thinking of a function of two variables, we're thinking of this surface as represented by a level surface of a function of three variables. Okay, so keep that in mind. Now let's say we're interested in finding this tangent plane at x naught, y naught. If we know x naught, y naught, we can find z naught using the equation of the plane, so that's fine. Now we want to try to find the normal vector to the surface. The way we're going to do that is we're going to take r of t, so let's say we've got a curve on the surface, and that curve is given by r of t equals x of t, y of t, z of t. We're going to take this parametric representation of this curve C that's on our surface, and we're going to compose it with this function f of x, y, and z. So we know when we're on this surface f of x, y, and z equals 0. Now if we're on this curve on the surface, well then x on that curve is given by x of t, and y on that curve is given by y of t, and z on that curve is given by z of t. So this is a curve on the surface. If we're on the surface, x of t, y of t, and z of t satisfy this equation. So I can take the composition of the two functions, and I get this. Now we haven't talked about differentiability yet of functions of several variables. We will shortly, but notice now this is a function of t only. I've replaced all the x's with some function of t. I've replaced all the y's with a function of t, and I've replaced all the z's with a function of t. So now if I take the derivative of both sides, using the chain rule, well, you'll see something interesting happens. Well, according to the chain rule, the derivative of this composite function is the gradient of the outside function, evaluated at the inside function, dotted with the derivative of the inside, and the derivative of the inside, we're going to think of that inside function as r of t, and we're taking the derivative of r of t, so that's going to be x prime, y prime, z prime, or altogether, we'll call that r prime. And that equals the derivative of 0 with respect to t, which is of course 0. So now we're saying, okay, well what does that mean? Well, this tells us that if r of t is on the surface, and it has components x of t, y of t, and z of t, and since it's on the surface, we can substitute that into this equation, and we're still going to get 0 because f of x, y, z equals 0 on this surface. Then, if that's true, and f is differentiable, and we'll talk about what that means in a little bit, then the gradient of capital F dotted with r prime of t equals 0. And remember what a dot product means from the very beginning of the course. If the dot product of two vectors is 0, that means those two vectors are orthogonal to each other. At every t, oops, just writing the same thing again. The gradient is orthogonal to r prime. This is true at every t. We're particularly interested in the t value that gets us here at x naught, y naught, z naught. So let's plug in a particular t value. Let's call it t naught. So the gradient at that point, x of x naught, y naught, z naught, which is given by x of t naught, y of z naught, z of t naught, the gradient at that point is orthogonal to this. Orthogonal, you know, we use orthogonal when we're talking about vectors, but we could also say perpendicular. We could say that these meet at a right angle. All we're saying is that this vector is at a 90-degree angle to this vector. So, okay, well, what does that mean? Well, remember what this vector is? I hope so. If this is position, I know you guys are thinking, that's velocity. What does that have to do with the geometry? Don't think about it in terms of motion. Think about it in terms of geometry. R prime is also the tangent vector. and we're evaluating it at t naught. So this is telling us that the gradient evaluated at x of x naught, y naught, z naught is perpendicular to that particular tangent vector at x naught, y naught, z naught, which is the same as evaluating the tangent vector at t naught. Now let's go back up here and think about what all of this means. Now, this was just some general curve on the surface. So we've got our surface, it looks like this. We said we're here. That's x naught, that's y naught, that's x naught, y naught, z equals 0. Then we evaluate the function at x naught, y naught, and we get x naught, y naught, z naught. Oops. And we said this curve r of t is a curve that lies on the surface and it passes through this point. So there's r of t. What we just did here by the chain rule tells us that if r of t lies on the surface and it passes through x naught, y naught, z naught, then the tangent vector evaluated at t naught, so the tangent vector that's going like this along that curve, it's also along the surface, that tangent vector is orthogonal to this gradient vector. And what I think is really cool is we did this in general for any r of t. So it works for that r of t, and it works for this other r of t and its tangent vector, and it works for another r of t. Oops, it should have passed through the point. And its tangent vector. It works for every r of t that lies on that surface and passes through that point. So what does that mean? That means the gradient evaluated at this point is perpendicular to all of the tangent vectors, or I guess I should say orthogonal. It's orthogonal to all of the tangent vectors. And that's kind of a big deal. Aren't you glad we studied the chain rule now? Look what the chain rule got us. Because of the chain rule, now I was able to derive the normal vector to a surface. This vector is perpendicular to all of the tangent vectors, so it's perpendicular to the tangent plane, or normal to the tangent plane. So that means the normal vector is equal to that, or we could say it's just parallel to that, because we can always change the length. Multiply by a constant to make the normal vector look a little bit nicer and cleaner. So that's kind of a big deal. So this can be our normal vector if we want it to be, or we could multiply it by a constant. It's going to give us a normal vector to the surface. If you don't remember why that works, like let's say this was 1/2, 1/2, 2. Like I don't want my normal vector to have a 1/2 in it. I might multiply everything by 2 to get rid of the fractions. That's all I'm saying when I'm saying it has to be parallel. Changing the length is not going to change the direction of that normal vector at all. So we can use this as our normal vector, and of course we can multiply by constants as we want to make the coefficients look nice. So that's going to be our normal vector to the surface. So this is one of the normal vectors to the surface, and we can always simplify. Okay, well now we've got everything we need. We needed two things. We needed a point on the surface. They're going to give us x naught, y naught. We can always find z naught, so that's great. And then we needed a normal vector. And remember how we do that. In order to find the normal vector, the first thing you have to do is find this guy. You need a function of 3 variables, x, y, and z. So you're taking your equation of your plane, or excuse me, of your surface, and you're just rearranging it. You're just doing z minus this to get f of x, y, and z by itself. So I just took this, I subtracted the x squared and the y squared from both sides, and I got this. So rather than thinking of this as a function of 2 variables, I'm thinking of it as a level surface of a function of 3 variables. We get that. The normal vector to the surface is just the gradient of this evaluated at x naught, y naught, z naught. Okay. So we got the 2 things that we need. Now we can apply that to actually find the normal vector to a surface that we're familiar with. So here's our first example. I've got 9, or z equals 9 minus x squared minus 4y, or excuse me, minus y squared over 4. And we want to find the equation of the tangent plane at this point x naught, y naught equals 2, 1. Or excuse me, 1, 2. I'm saying everything just a little bit backwards today. Sorry about that, guys. All right, so let's think about what that surface looks like. Well, I've got an x squared and a y squared. Z is raised to the first. Since both of these have the same sign and z is raised to the first, this is an elliptic paraboloid. Since both of these are negative, it's like we took our regular elliptic paraboloid, we multiplied it by -1, so it flipped the whole thing upside down. Then we added 9 to it, and it shifted the whole thing up 9 units. So this is what we've got. Oops. Here's our x-axis, our y-axis, and our z-axis. We go up 9. It's going to look like this. It's longer in the y direction than it is in the x direction. And I'm only drawing part of it. It actually goes down past the xy plane. It goes on forever. The range is -infinity to +9. So this is just the part of it that I'm sketching. Now, we're interested in the tangent plane to the surface at x equals 1, y equals 2. So at x equals 1, y equals 2, let's find out what z is. So I have 9 minus 1 squared minus 2 squared over 4. So that's 9 minus 1 minus 4 over 4 is 1. So we get 7. Z is 7. So x equals 1 and y equals 2. And it'd be up 7 units. So we're at 1, 2, 7. And we want a tangent plane right there. Of course, I'm just showing you a little patch of the tangent plane, not the whole thing. It doesn't look very tangent to the surface. I'm sorry, guys, but that's the idea. We want the tangent plane at 1, 2, 7, which is approximately right there with my very rough sketch. Okay, so how do we do it? The first thing that we do whenever we want to find the tangent plane to the surface is we find a function of 3 variables, f of x, y, z. I'm saying find, but you're really just rearranging the original equation. I guess we're computing f of x, y, z, and that will be given by z minus f of x, y. And of course, we're talking about a level surface of this function of 3 variables. If I rearrange f of x, z equals f of x, y, this way I get z minus f of x, y equals 0. Okay, so here is my function of 2 variables, little f of x, y. So I'm just going to subtract this from both sides to get z by, or to get one side set equal to 0. So we'll have z minus 9 plus x squared plus y squared over 4 equals 0. So instead of representing our surface this way, we're representing our surface this way. Okay. You write it down here. All right. And now we just need to find the gradient of capital F. And we want to evaluate it at the point of interest, but I guess we'll just call that a separate step, excuse me. Since f is a function of 3 variables, we've got a vector of first partials over here. We're just going to take the first partial of this with respect to x, with respect to y, and with respect to z, and those are the components of our gradient vector. This does not have any x's in it, so its derivative with respect to x holding y and z constant is 0. Derivative of that is 0, derivative of that is 2x. There's no x here, so it's a constant, its derivative is 0, so we just get 2x. Partial with respect to y is similar. I don't think I'm going to write this time. Derivative of that is 0, that's 0, and that's 0, because there are no y's in those terms, so those are gone. And then the derivative of this guy with respect to y is 1/4 times the derivative of y squared with respect to y, which is 2y. So we get 1/2 y. And the partial of f with respect to z is 1. Minus 0 plus 0 plus 0. So we just get 1. So our gradient is the vector with components 2x, 1/2 y, and 1. Okay. And to find the normal vector, we want to evaluate this. At the point, and I guess this is really more of a 4th step because we found the point earlier. I forgot to outline that in our method. If x equals 1, we get 2. If y equals 2, we have 1/2 times 2 is 1. And of course, we've got a 1 there. These are nice small integers, so that's a good choice for the normal. We're going to let the normal equal that. Those are the values of a, b, and c, the coefficients of our tangent plane. And then we just substitute a, b, c, and x naught, y naught, z naught into the formula for a plane. So the formula for a plane was just a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0, where a, b, and c are the components of the normal vector, and x naught, y naught, z naught is a point on the plane. So the tangent plane is just a special case of a plane. To find the normal, we took the gradient, we evaluated it at the point. That's our a, b, c. So we can substitute a, b, and c in down here. Oops. A is 2, B is 1, and C is 1. And then we substitute in x naught, y naught, z naught. X naught, y naught, z naught was 1, 2, 7. So we're done. That's the equation of a plane. I probably wouldn't leave it like that though. Let's simplify this a bit. So we'll distribute the 2. Distribute the 1, which doesn't do much. Distribute the other 1. And then you want to get all the constants on one side. Negative 2 minus 2 is negative 4. Negative 4 minus 7 is negative 11. So our equation is 2x plus y plus z equals positive 11. That's the simplified form. That's what we're calling general form in this course. So that's the equation of the plane. So here's our plane. It has equation 2x plus y plus z equals 11. Now, I forgot a step in my outline of the method, so let's go back. I'm going to call this step 2, and this step 3, and this step 4, and this step 5 now. What was our first step? Well, they gave us x naught, y naught, and the first thing we did was, if that's x naught, y naught, we wanted to find z naught, so we found z naught. So that's your first step. Okay, so we were asked to find the equation of the tangent plane. How do you do it? Well, if they give you x naught, y naught, find the corresponding z. Now you've got your ordered triple x naught, y naught, z naught. That's your point in the plane. Now you just need to find the normal vector. To find the normal, you have to define this function of 3 variables, f of x, y, z equals z minus f of x, y. You could also do f of x, y minus z. That'd be fine too. I like to do it this way though. So I take z and I subtract the right-hand side of the equation defining the surface, and I distribute. Then I find the gradient of that function, and then I evaluate it at the point. That's a normal vector to the surface. If we didn't like fractions, or if it was just ugly for some reason, maybe it's negative for our a value and you want it to be positive, you can multiply this by any constant you want, and it's still going to be normal to the surface. It's just going to have a different length, and if you multiply it by a negative, it'll point in the opposite direction. So you get the normal, and once you have the normal and the point, you just substitute into the equation of the plane and simplify. That's it. Pretty simple. Okay, let's do one more example with a familiar surface. So let's say we have 9x squared plus y squared plus 4z squared equals 36. And they ask us to find the tangent plane at 1, square root of 11, and 2. I know it's a little odd, but it was just the y value that was necessary in order to get 36 over there. Okay, now this is a little different. Rather than giving you z equals a function of 2 variables, this time we're already given a function of 3 variables. But it's a familiar function, or a familiar surface. Notice the x, y, and z are all squared. All 3 are positive, and we have a 36 on the right-hand side. So since all 3 are squared and all 3 are positive, and we've got a constant over here, this is an ellipsoid. We know that. We just have to rearrange it so it looks more like an ellipsoid. The formula for the ellipsoid had a 1 on the right-hand side, so we'll divide both sides by 36 to write the equation in standard form. It will just make it a little easier for us to graph. Now, if you're asked for the tangent plane, you do not have to graph the surface. I'm just graphing the surface so that we can kind of see what's going on, see what it is we're calculating. In another video, we'll have some surfaces where we don't have that luxury. I wanted to give you one video where you could actually see a point on the surface and then see the tangent plane. Okay, 9 goes into 36 4 times, 4 goes into 36 9 times, so I'm simplifying those guys, and I've got this. So this is definitely an ellipsoid, and if we want, we could write it this way. I'm writing those denominators as a squared, b squared, and c squared to make it even easier to graph. It's got an ellipsoid centered at the origin. And we want to graph this thing. Okay, well, it looks like we go plus and minus 6 units in the y direction. and we go plus and minus 2 units in the x direction. So when z equals 0, we get an ellipse that looks like this. And we go plus and minus 3 units in the z direction from the center, which was 0, 0, 0. Okay, so that's our ellipsoid. What is it we were doing again? Oh yeah, we're finding a tangent plane. At this point, x equals 1, y equals square root of 11, which is a little bit more than 3. It's a little bit more than square root of 9, right? And then z equals 2. So we'll go 1 unit in the x direction, 2 units in the y direction, and then, or excuse me, not 2 units in the y direction, 1 unit in the x direction, about 3 units in the y directions, and 2 units in the z direction. And we'll have a point right here. And we want a little tangent plane right at that location. I'm going to highlight my plane. All those curves, all those traces in our different coordinate planes. It makes it a little bit harder to see. That's the plane that we're looking for. And again, it passes through this point 1, square root of 11, and 2. Okay, so we were given the point this time. We didn't have to find the z value. So all we have to do this time is find capital F and find its gradient. Well, since we weren't given z as a function of 2 variables, we already have capital F here, almost. We're used to setting capital F equal to 0, so you could subtract the 36 from both sides. Or you could think of this as a level surface of capital F equals this, and it's a level surface f of x, y, z equals 36. But we're going to stick to our convention, so we'll set one side equal to 0. I'm going to say find capital F of x, y, z such that f of x, y, z equals 0. And that's just a convention, just a personal choice. So we take our equation and we subtract the 36 from both sides so that f of x, y, z equals 0. Then we find the gradient and evaluate it at the point. That's our normal vector. Or that is a normal vector. And if we like the form of it, we'll keep it. If not, we'll multiply or divide by a constant to make it look cleaner and prettier. We want small integers that don't have any factors in common, usually. So let's find capital, or the gradient of capital F. I need partials with respect to x, y, and z. Those are pretty easy to find because of the form of our surface. The derivative of this with respect to x is 18x. There's no x here, here, or here, so the partials of those 3 terms with respect to x are all 0. Partial of this with respect to y, it's 0, 2y, 0, and 0. And the partial of this function with respect to z, there's no z's, so that's 0, 0, 8z, and 0. All right, now we want to evaluate it at this point, 1, square root of 11, and 2. So you replace the x with square root, or with 1, you replace the y with square root of 11, and you replace the z with 2. And I don't think we're going to be able to do anything about that square root of 11. That's okay. So we've got 18, 2 root 11, and 16. Well, that could be my normal vector, but I'd like my equation of the plane to be as simple as possible, so I prefer that these three components don't have a common factor. They all have a common factor of 2. So I'm going to let the normal be half of that. Now you can choose any constant you want, or you could just use that as the normal vector. That would be fine. Half of that's going to give me 9, square root of 11, and 8. That's our ABC. So we've got a point, x naught, y naught, z naught. It's right here. We've got a vector ABC with components right there. You just substitute those into the equation of a plane. Okay, so I have this as my standard form of the equation of a plane. Hope I'm not going too fast. I drank a lot of coffee today. It's one of those days where second cup of coffee felt right. Okay. So I'll substitute my A, B, and C first. Those are the components of the normal. A is 9, B is square root of 11, C is 8. And then I'll substitute x naught, y naught, z naught next. X naught, y naught, and z naught were up here. 1, square root of 11, and 2. And then we simplify. If I just ask you for the equation of the plane, you could stop here, but that's just not a very nice form to leave the plane in. So we'll distribute the 9, distribute the square root of 11. Square root of 11 times square root of 11 is 11. Distribute the 8. And then simplify where you can. Negative 9 minus 11 is negative 20. Negative 20 minus 16 is negative 36. So I've got ax plus by plus cz equals, and when I add those together, I get negative 36. I'm going to add them to the other side, so I have positive 36. Well, I'm adding them to both sides, and that's giving me a 36 on the right, technically. Okay. So that's the equation of my plane. That yellow plane over here has this equation, 9x plus square root of 11 times y plus 8z equals 36. And again, how we did it was we took this equation. This part wasn't necessary, but to graph it, to see what was going on, we wrote the equation of the ellipsoid in standard form. We graphed it. We were told to find the tangent plane at this point. So we plotted that point on the surface, drew a little tangent plane, and we said, okay, what do we need? We need a point, which they gave us, and a normal vector. So first we found capital F of x, y, z. Now, normally we've got z as a function of 2 variables, and so we move everything over to one side. This time we didn't. We just had a surface given to us this way. So we just set one side equal to 0 just because of convention. And now that's f of x, y, and z. So we got that. Take its gradient, evaluate it at the point. That's a normal vector. I wanted a normal vector with sort of nicer coefficients, so I divided by 2 or multiplied by 1/2, and I got this. Now you could have just as easily used that as your normal down here. Just the whole equation would be the same, just multiplied by 2. So I used the simplified version of the normal. And I just substitute. my a, b, and c, substitute my x naught, y naught, z naught, simplify, and I get the simplified equation of the plane. So that's easy breezy, and we can see what's going on in another video. We'll do the same thing with a couple of surfaces where we can't see what's going on. We don't know what the surfaces look like without technology. But the principles and for finding the equation of the tangent plane are exactly the same.